Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about Newton's first and second laws, two of the most fundamental laws that we will be encountering all term. And throughout this discussion, we will refer to the first law by the shorthand N1 for Newton force law number one, and we'll call the second law N2. And at the heart of both these laws is the basic idea that forces cause acceleration. That's the basic content. And one is if no force, then there's no acceleration. So if the force is equal to zero, the acceleration is zero. That means without a force, an object travels with constant velocity. And then N2 is that the acceleration of an object depends on the force, the net force that acts on it. And it also depends on the mass of the object, which is a measure, sometimes the mass is called the inertia of the object, which is a measure of its tendency to resist acceleration. So objects with a big mass for a given force, have a smaller acceleration. Now, you might say, well, wait a second, why do you need two laws here? Because if you look at Newton's second law and you set the net force equal to zero, that predicts that the acceleration should be zero. So why do you need Newton's first law? That basically, it looks like a sort of a special case of the second law. And, for practical purposes, that's mostly true. But there is sort of a subtlety about why the first law actually has some important content to it. But let's hold that thought. We'll get back to that at the end of this episode of What's the Big Idea. So the second law in particular, it looks very simple. I mean, it's just so simple to write down, and yet it's a source of tremendous subtlety, and it really takes a lot of practice doing problems before you will appreciate all those subtleties. So you'll have a chance in the coming weeks to do lots of problems in which the basic physical law that's at the core of solving the problem is Newton's second law. And then as a first example, we'll consider, the Galileo experiment. You have a ball here that's in so-called free fall, where the only force that acts on it is the force of gravity. So, if we were to draw a diagram of what's going on when the ball is falling, we would represent we're drawing what's called a free body diagram here. And the only force that acts on the ball is the force of gravity. So the acceleration of the ball, according to the uh, second law, should just be the net force, which is just the force of gravity, divided by the mass of the ball. Now, it turns out that the force of gravity, um, according to Newton's law of gravity, is just proportional to the mass of the ball. Near the Earth's surface, the force of gravity is just the mass of the ball times this vector g. So we find that um, the masses cancel and the ball falls with a constant acceleration of 9.8 meters per second squared in the downward direction, independent of its mass. So this simple example illustrates, the power of Newton's second law, because it says that if you know the force that acts on an object, you know its acceleration. And then we know from our previous discussion of kinematics that once you know the acceleration of an object at all times, you can calculate its velocity at all times. And then if you know the velocity at all times, you can calculate the position. So Newton's second law really provides a route for letting you calculate the motion of the object. That's really the big idea behind the second law. Now, another sort of situation you can encounter, the example we just gave is we were, knowing the force that acted on the object, we could calculate its acceleration. There's another class of problem which you'll encounter quite often, and which is you're sort of given information about the acceleration of the object, and then you can use N2 to figure out something about the forces that must be acting on the object. So, we could just obviously rewrite N2 as F net equals ma. And in that case, we can think of, if we're given a, the acceleration of the object, and we also know the mass, we can say something about the net force that acts on the object. So let's give a couple of simple examples. So in this first example, I've got a book, and it's sitting on a table, and the book is at rest on the table. If it's at rest, it's not moving. That certainly means that its acceleration is zero. So that must mean that the net force that acts on the book must also be zero. Now, how can that be? Well, the net force is the sum of all the forces that act on the book. So now we just have to identify the individual forces that act on the book. So now we draw what's called the free body diagram. Will represent the book by a little dot, and we have to identify the individual forces that act on the book. Well, one of the forces is the force of gravity, and that points downward. And as we just said, the force of gravity is just equal to m, the mass of the book, times this vector g, which is a vector of length 9.8 meters per second squared, and pointing in the downward direction. Now, we've said we know in this situation that the net force that acts on the book is zero, because the book is not accelerating. So there must be another force that acts on the book that we can add to the force of gravity, and so that the sum of the gravitational force and this other force adds to zero. And the other force in this case is, of course, the force that the table exerts on the book. So we'll call that the force of the table on the book. And that has clearly got to be directed upward, and its length has got to be the same as the length of the arrow that we drew for the gravitational force, but it's just directed in the opposite direction. And when you add these two forces together, we're going to clearly get zero. Now, you may be wondering, how does the table know to exert exactly the right force to cancel out the force of gravity? How is it adjusting its force to do just the right thing? Well, maybe it'll help to think, instead of thinking of a table, let's draw essentially the same situation, but just a little bit different. Imagine you've got a platform with a spring on it, and the book is resting on this platform, which is connected to a spring. And a spring is an object, as we'll discuss a lot more in the future, is an object that the more you change its length, the greater the force is. So as you compress a spring, as you compress the spring downward, it's going to exert an upward force whose magnitude is proportional to how much you've compressed it. So what ends up happening in this situation is you rest the book on this platform, which is connected to the spring, and it may take a little bit of time for the things to settle down, but basically the spring compresses just the right amount so that when the book comes to rest, the spring force pointing upward is exactly canceling the gravitational force pointing downward. And that's essentially the situation that is in play when we rest a book on a table. You can think of a table as just a very stiff spring. So these so-called contact forces that exist between, say, a tabletop and a book are really, at the end of the day, nothing more than really spring forces. You could think of solid materials as just basically made of atoms connected to one another by springs, and when you rest the book on the table, those springs compress just a little bit. And because those springs in the tabletop are so stiff, you don't even notice it. And the movement is very small, but it's there nonetheless. And then, as another example of where you know something about the acceleration, and you can use the second law to determine the net force that must be acting on the object. Let's consider this case of uniform circular motion, UCM. in which you've got, say, a rock on a string, and you're twirling the rock. This is, say, a top view, and the rock is going around in a circle of radius r. So we know from our previous discussion that as the rock goes around in the circle, its acceleration, the magnitude of the acceleration, is just the speed squared over r. And the direction is pointed radially inward. Um, so uh, that must mean if the rock is going around in a circle at speed r and the circle has a radius r, the second law tells you that the net force that acts on the rock must be equal to the rock's mass times v squared over r. And I'll give the direction. I'll just write the word here. It's a vector quantity, so the direction points radially inward. And in this case, the only force that's acting on the rock must be the force that the string exerts on the rock. So you can think of the string again as like a sort of a stiff spring, and it basically is adjusting its length as it goes around so that it is always exerting an inward force of magnitude mv squared over r. So there's one last subtlety about the Newton's second law that I want to at least get you thinking about now. Uh, so imagine the following situation. Imagine you've got a little rocket ship with an engine, and you have a ball in the rocket ship. And imagine that the rocket ship and the ball are in deep outer space somewhere, and they're just stationary. There's no gravity. Both the ball and the rocket are just standing still. Okay? And then imagine what would happen if all of a sudden you turned on the rocket and the rocket started accelerating. So if stuff comes out of the back of the rocket is going to accelerate in the direction towards the top of the screen. And uh, relative to the rocket, the ball, if we were looking at this from the outside, the ball would just, continue to be at rest and the rocket would be accelerating upward. But if you were standing inside the rocket watching what would happen, would relative to the rocket, the ball would appear to be accelerating downward. And even though there are no forces acting on the ball, there's nothing touching the ball, there's no gravity in the story. So the ball has no forces acting on it, and yet relative to the rocket, the ball would appear to be accelerating. And that seems to contradict what we know about the first and second laws, but it's really not a contradiction because implicit in the first and second laws is the idea that we're making measurements relative to what we're going to refer to as an inertial frame of reference. And that just means that the coordinate axes that we're measuring things with respect to are not accelerating. An inertial means a non-accelerating frame of reference. So the first and the second law, all of Newton's laws, make sense only if we limit consideration to inertial frames of reference. And later on, before too long, we're going to be dealing with things like falling elevators or orbiting rockets, which are not inertial reference frames. So we just have to keep in mind that when we do that, when we have these non-inertial frames, Newton's laws need to be amended somehow, and we'll deal with that down the road. But I just wanted to get you thinking about it at this early stage. So that gets back to the point I made at the beginning of this, episode slide about Newton's first law. Remember, Newton's first law seemed like it had no new content. It seemed like just a special case of the second law. But now, really, what you can think of the first law is the first law basically can be written, and we can say that N1 So a formally correct statement of Newton's first law of motion is would be something like this: if you view things from an inertial frame of reference, in that case, then if there's no net force acting on the object, then the acceleration of that object will be zero. So you can think of Newton's first law basically as helping to establish a test for whether the frame that you're dealing with is an inertial frame of reference. And then if it is, Newton's second law will be valid. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.